Today we're going to be looking at proving some theorems. So yesterday we began looking at what a proof looks like with its two-column format and with our statements on one side and the reasons on the other, and how we progress through the logic of a proof. So today we're going to look at a couple of theorems and what the proofs of those look like. Our first theorem is called the midpoint theorem. It says if M is the midpoint of segment AB, then AM is half of the full length AB, and MB is also half of the full length of AB. It's important here that we distinguish how this is different than our midpoint definition. We defined a midpoint back in chapter 1, and the definition of a midpoint is that it breaks a segment into two congruent pieces. So that would be saying that AM is exactly the same size as MB. This is taking it beyond that to say that each of those pieces is half of the full length. So to prove this, we need a given and what we're supposed to prove. In an if-then or conditional statement that we learned about in lesson 1, in an if-then statement, our given is the if portion. So we're given M is the midpoint of AB. The then portion is what we're trying to prove. So we're trying to prove AM is half of AB and MB is half of AB. So we said yesterday a good way to begin a proof is with the given. So we're going to start by saying M is the midpoint of AB. And that's our given. So then one question I ask myself often when I'm writing a proof is, so what? So what does that tell me? Where can I go from here? So knowing that M is the midpoint of AB, I can apply that definition of midpoint and say that then AM should be equal to MB. Our definition of a midpoint was that a midpoint makes two congruent or equal pieces. So now this is good because I'm bringing AN and MB into it, but I want to know how they're related to AB. So what I can do is say that AB is equal to AM plus MB. AB is the full length, putting together those two smaller pieces. And this one we learned back in chapter 1, but we also applied it yesterday in some of our problems. This was called our segment addition postulate. And we can add together two little segments and get a bigger segment. So now this is good because I have AB back in the problem, which I need for our destination, keeping in mind what we're trying to prove. But I've got AM and MB. In the previous step, we said that AM and MB are actually exactly equal to each other. So what we can do is use them interchangeably then. And I'm going to say, instead of saying MB here, it's really the same thing as AM. So I'm going to rewrite step 3, but saying AB is AM plus AM. Or I could say that AB is then 2 AMs. Our reason here, we have to think about what we did. We rewrote step 3, except we swapped out the MB for the AM. And when we switch something out, that is our substitution property. So now if we look at what we have in step 4, and the first thing that we're trying to prove, that AM is half of AB, this seems really close. We've got the AM, we've got the AB, but we've got a 2 instead of a half. So if we think about this like an algebra problem, I can get that 2 over to the other side, and it would become a 1/2 AB is equal to AM. And in algebra, what we just did was divide. We did our division property of equality, dividing both sides of this last equation by 2 to turn that into a 1/2 on that left side. So that's half of what we're trying to prove. That's the first thing we're trying to prove. The good news about this being half is we don't need a whole nother 5 steps. We're actually almost done, just one more step to finish this out, because if we look at step 5, and the other thing that we want to prove is that MB is 1/2 of AB as well. Well, AM and MB are the same, so I can just swap that out for an MB and be done with it, since AM and MB are actually equal to each other. So when I swap something out, that's a substitution property. Okay, so this is the proof of our midpoint theorem. So again, the midpoint definition tells us we get 2 equal pieces. The midpoint theorem tells us that we have half of the whole, that each piece is half of the whole length. So here we're not going to write a proof, but we're going to say what kind of things could we prove about this. This word deduce, it says what can we deduce? It means what could we prove, or what could we figure out, or what could we say about this picture. So given that M is the midpoint of AB and N is the midpoint of CD, what are some things that we could say? Well, we could say that AM equals MB. That would be our definition of midpoint. We could say that AM is half of AB, or likewise that MB is half of AB. Those would be our midpoint theorem that we just proved. We could say those same things about the other piece. We could say that CN is equal to ND, or we could say that CN is half of CD, or that ND is half of CD. But a crucial thing that we cannot say is any relationship between the 2 separate pieces. So we can't say something like AM equals CN, because we don't have any relationship to combine the 2 pieces of information. So we've got 2 separate segments, and there's nothing that tells us about them together. So we have to be careful that we're not extending too many equal signs here. We can say stuff about the first segment, each half of that. We can say stuff about the second segment and each half of that, but we can't say anything about the 2 segments together. Our next theorem is called the angle bisector theorem. It says if BX is an angle bisector, then each of the 2 angles that it makes are half of the whole angle. This is almost exactly the same thing as the midpoint theorem, except the midpoint theorem is talking about segments and the angle bisector theorem is talking about angles. But both of them are talking about halves of wholes. So that means our proof for this is actually going to be almost exactly the same as our proof for theorem 2.1, the midpoint theorem. So as we write this out, keep looking back to what we had written in that first one, and you're going to notice a whole lot of similarities here. So once again, the if is our given part. The then is what we're trying to prove. So we're going to begin by saying BX bisects angle ABC as our given. Then, I want to say, where can we go from here? Well, we could ask ourselves, what does it mean to bisect? So our definition of angle bisector that we learned back in chapter 1 is that it makes 2 equal angles. So we can say the measure of angle ABX is equal to the measure of angle XBC. That's what it means to be an angle bisector, so that's the definition of angle bisector. Then if we're comparing this back to that first one that we did, the next thing we applied was looking at the picture to say, well, how can we talk about the whole thing? And we applied our segment addition postulate. We're going to do that same thing here, except this problem's talking about angles. So we're going to apply our angle addition postulate and say the measure of angle ABX plus the measure of angle XBC is equal to the measure of angle ABC. The two parts add up to the whole, according to the angle addition postulate. Then again, if we're comparing this to the first one, what we did is now we wanted to combine our information of steps 2 and 3, saying in step 2 we said two things are equal. In step 3 we talked about those things again, so we might as well stop using two names when one will do. And instead of saying ABX and XBC, we can plug in one for the other. So we're going to say the measure of angle ABX plus the measure of angle ABX, switching out that XBC for an ABX because they're equal, is the measure of ABC. Since we switch something out, that's our substitution property. Now in this same step I can rewrite this. I didn't have room to include it on the same line, but I can combine those two things and say that instead of writing it twice, I have two measures of ABX is equal to the measure of ABC. So if I'm trying to show that ABX is half of ABC, I've got that 2 on the wrong side, so we can apply some algebra here and divide both sides by 2. That gets our measure of ABX alone and puts a 1/2 over on that other side. So again, moving from that last step, moving from step 4 to step 5, what we did was an algebra step of divide both sides by 2, and that gives us a 1/2 over with the ABC. And we were really asked to prove two things here. We were asked to prove that ABX is half of the whole angle, but also that XBC is half of the whole angle. But since ABX and XBC are actually equal to each other, I can take this guy and swap him out for the other thing we're looking for, an XBC. So that gets me, my measure of XBC is 1/2 the measure of ABC. Since it was swapping something out, that's our substitution property. Once we have proven a theorem, that theorem can now start to become a reason in other proofs. So types of things that we might have as reasons in proofs. We're going to use a given. We could have definitions. We could have theorems. We could have properties like addition or substitution. And we can have postulates like segment addition or angle addition. But once we've proven a theorem, that also can be a part of our reasons as well. So here we're asked to prove something. We're given that EG is the bisector of angle DEF and that SW is the bisector of angle RST. And what we want to prove, oh, and also that DEG is equal to RSW. What we want to prove is the whole of DEF is equal to the whole of RST. So a good place to start is with a given. Now this given has a lot of information. There's really two different types of information. There's two statements about bisectors, and then there's a third statement, a second type of statement that's about equals or congruence. So sometimes when I have different types of givens like that, I like to split them up, and so I'm just focusing on one thing at a time. So I'm going to begin by just saying EG bisects angle DEF, and that SW bisects angle RST. But I'm going to hold off on that last piece of the given until I feel like I'm done with what I can do here. It's not wrong to include it all in the beginning, just sometimes it helps me process through one thing at a time if I hold off. So now I can ask myself, what does it mean to be a bisector? Well, we could do a definition of bisector here and talk about how we'd have equal angles. Or now that we proved this angle bisector theorem, we can actually use that as well. And that's what I'm going to choose to use here. And I'm going to say that the measure of angle DEG is 1/2 the measure of angle DEF. So that looking at the picture, kind of the upper piece is half of the whole thing. And likewise for the other picture, the measure of angle RSW is equal to 1/2 the measure of angle RST. So that was our angle bisector theorem. So once we've proven that theorem, we're allowed to use it as a reason. Now I feel like I'm kind of stuck here, so I'm going to bring in that other given and say that the measure of angle DEG is equal to the measure of angle RSW. So again, it wouldn't have been wrong to put that all in step 1. That would have been a fine thing to do. It would have made our proof actually one step shorter, but sometimes it helps me to just think about one thing at a time. So now, in steps 2 and 3, we've listed a lot of angles here. So what I want to do is try to see if I can set up some sort of a chain to get myself from one piece to another piece. So I know that DEG is here and here. I know that RSW is here and here. So if DEG and RSW are equal, then anything that they equal must also be equal to each other. So what we can do is say these two things over here must actually be equal to each other as well. So kind of everything in steps 2 and step 3 are all equal to each other. So I'm going to say 1/2 the measure of angle DEF is equal to 1/2 the measure of angle RST. And that's a substitution. We could also, as a reason, give the transitive property here, and that would be acceptable as well. Whenever we have this equals this equals this equals this, everything's equal, that can also be called our transitive property. So we're not quite done, but if we keep that destination in mind of what we're trying to prove, we're trying to prove DEF equals RST. Well, I just said half of DEF is equal to half of RST. So if we think of this like an algebra problem, then we can get to our final step. I kind of ran out of room, so I'm going to scooch over and put step 5 a little bit over to the side here. But we want to end by saying DEF is equal to the measure of RST, because that's what we were asked to prove. And then our reason for that is whatever sort of algebra we would think about doing here. So one way to get rid of that half on both sides would be multiplying both sides by 2. Another way we could say is we divided both sides by 1/2. So we could say this is either the multiplication or the division property of equality. Sorry, again, kind of squishy there. I ran out of room. So what we've been practicing in these problems is deductive reasoning. Deductive reasoning is proving statements based on givens, definitions, postulates, and theorems as long as we've already proved them. So deductive reasoning is based on facts. It's not based on observations or feelings or intuition. It's based on facts, and that's what we're going to be focusing on here. So now we have some problems where we want to justify the statements. Remember, justify is like what would go in that reason column. What's the definition, postulate, or theorem that would allow us to say this? So our first one here says that I take angle AEB and add it to another angle BEC, and I get angle AEC, a bigger angle. An angle plus an angle, that looks like the angle addition postulate. The next one says segment AE, the length of AE, plus the length of EF is the length of the whole thing AF. A segment plus a segment, that would be our segment addition postulate. The next one says angle AEB plus angle BEF equals 180. If we kind of highlight those out in the picture, we've got AEB plus BEF, and together they make a straight line, which a straight line is 180. But I'm still adding an angle plus an angle. So that would still be my angle addition postulate. It's just that special case of the angle addition postulate where instead of just making a general angle, they're making a straight angle. Question 4 says, if E is the midpoint of AF, then AE is congruent to AF. So one way to think about these justified problems and find an answer is to look for any keywords. So I've got a keyword of midpoint here, and then I've got a congruence. When we're talking about congruence, that's going to be a definition. So this is going to be our definition of midpoint. This problem looks really similar to the next one. Number 5 still has that keyword of midpoint, but instead of talking about congruence, we have this half in here. When halves start showing up in the problems, that's going to be one of the theorems that we talked about today. So this is going to be the midpoint theorem. Theorems have halves, definitions have congruence or equality. If E is the midpoint of AF, then EC bisects AF. So if E is the midpoint of AF, then EC, this ray, bisects or cuts AF in half. This one's kind of tricky because that really has two keywords in there, midpoint and bisects. We're going to focus on this word bisect, and this is actually our definition of bisect. We learned the definition of bisect back in chapter 1, and we haven't used it very much since then. But our definition of bisect said something, so in this case a ray, that goes through a midpoint. So that bisector goes through the midpoint E. The next one says, if EB bisects AF, then E must be the midpoint. So if EB is cutting AF in half, then E must be in the middle of that. This is almost exactly the same thing as the last problem, and it's still going to be our definition of bisect. Definitions work forward or backward. So we talked in lesson 1 about converses. Number 6 and number 7, question 6 and question 7, are pretty much converses of each other. They say the same thing but backwards. Definitions are true forward and backwards. Our next one has a keyword of bisector, and then it has a half in there. When you see a half, you know you should be looking at one of our theorems from today. So this is going to be our angle bisector theorem. Number 9 has a keyword of bisector and a congruence. A congruence is going to be a definition. So this is our definition of bisect, or specifically our definition of angle bisect. So definitions will have congruence. Theorems are going to have halves. Your homework for tonight is from section 2.3, 1 through 11, and 13 to 15.